Hello everyone. Today I want to start chapter 22. Okay. Chapter 22. This chapter is about the electrostatics. Electrostatics. So the electrostatic, it is simply the study of charge at rest. Okay. So let us start with the charges. So we have two types of charge, that is proton. This is positively charged and you can represent like this, P plus, this is proton. People they also use the simply like a E also. Okay. And electron, this is negatively charged and you can write down E minus. Okay. And there is another particles we call neutron. Neutron, it has no charge, it is simply neutral. Neutral, okay, no charge. Okay, so we have a positively charged, that is positively charged particles, that is proton, negatively charged particles, that is electron, and we have another particle, neutron, that is neutral, no charge. Okay, then if you draw the atom, okay, so draw the atom like this. The central portion of the atom we call the nucleus. Nucleus, this portion, this here, the central portion of the atom. Okay, this is called as nucleus, and in the nucleus, inside the nucleus, you have a proton P plus. Here it is really very small region, and there you have proton, and neutron you can write down N0. N0 is a neutron. And depending on the size of the atom, or like a different atom, they do have a different number of protons and different number of neutrons, of course different number of electrons also. Okay, so let me write down one proton and 0 neutron. So this is hydrogen atom. Hydrogen atom has only one proton and no neutron in case of hydrogen atom. That's why hydrogen atom is the lightest atom. And there is one electron. So this is the electron. So this is the hydrogen atom. Hydrogen atom. So hydrogen atom has one proton, one electron and 0 neutron. You know, it is the very first element in the periodic table. And if you draw the other atom like a helium atom, you have a 2 proton, 2 neutron like a helium. If you draw the helium, helium has a 2 proton and 2 neutron, and you have electron here, like 1 electron there, and somewhere you have another electron here, 2 proton and 2 neutron, and this is the helium atom. Similarly, hydrogen, first element, helium, lithium, beryllium, boron, you have many, you can the periodic table. Okay, so anyway, we don't want to do the periodic table here, but if you draw the atomic structure, like you can see the proton, you can see the neutron, and you can see the electron. But if the atom is in ground state, the number of proton is equal to the number of electrons. Okay, number of proton is equal to the number of neutron. That's why we say that atom is electrically neutral. Okay, so you need to know this. Atom is electrically neutral. What does this mean? This means number of proton which is positively charged is equal to number of electron which is negatively charged, because number of proton, like in case of, let's say here, helium atom, 2 proton, 2 electron, 2 protons, so 2 positive charge, and these 2 positive charge is cancelled by the 2 negative charge. That's why atom is electrically neutral. Okay, so this is about the proton, electron and the neutron. Simply the charged particles are only the proton and the electron. Now let us discuss about the properties of charge. Properties of charges. So the very first property is like charge repel and unlike charge attract. What does this mean? If you have a proton here, positive charge, and if you have another proton there, again positive charge, so they are like charge. What happens? If you bring the positive charge and positive charge close, they repel. So there is a repulsive force. They repel like this. Similarly, if you bring negative charge here and negative charge there, okay, they also repel because they are like charge. Same charge, like charge, similar charge, they repel. But unlike charges, like let us suppose here you have a proton, positive charge, and you have a electron, negative charge. What happens? They attract to each other. So you have to draw like this. They attract like this. So the proton and electron, they are opposite charge. They are unlike charge, so they attract. Proton and proton or electron and electron, they are like charge. They repel. So like charge repel. So there is a repulsive force between the two same charge, similar charge, like charge. But there is an attractive force between two unlike charges. If you have a positively charged particle here and negatively charged particle here, they attract. Okay. So this is the first property. And the second property is charge is conserved. What does this mean? Charge is constant. We cannot create the charge. We cannot destroy the charge. But we can separate them, but we cannot create. We cannot destroy them. That's why we say the charge is constant, charge is conserved. And the third property is charge is quantized. Charge is quantized. What does this mean? You know, the very smallest unit of charge is E. This is, you can write down, this is equal to 1.6 times 10 to the power negative 19, and the unit of charge is coulomb. So the smallest unit of charge is 1.6 times negative 10 to the power negative 19 coulomb. Now the charge you can write down like this in any particles. The charge is either you have 1 times E, 2 times E, 3 times E, 5 times E, like 11 times E, 15 times E, like 16 times E, multiple of like the integral multiple like this. Whole number 1E, 2E, 3E, 4E, 5E, 6E, like that. If this particle, like if you have to measure the charge, let us suppose if this is the charge particle, you can write down the charge on this object is 2 times E or 3 times E, 5 times E, but you cannot do like this. 3.2 times E, this is incorrect. Don't do this. Don't do this. So it is like a whole number here. So this is what we call the quantized. Just we do the property only here, so we don't have to go in detail. So charge is quantized. So this is another property. Okay. And you know, if you have a, let's say, if you take a object, this is a conductor. You know that conductor conduct electricity like a copper, iron, aluminum, they are conductor. And we have an insulator like a wood, sand, paper, plastic, they are insulator. So here I have a conductor like a copper sphere, and let us suppose I have positive charge here, positively charged there, like this. Okay, and here I have another one. This is neutral. This is again conductor, but this is neutral. But see, they are far. They are not very close. But what I would like to do is, I want to join these two spheres using the nail. This is iron nail. Okay, you know iron is a conductor. So I join these two spheres, copper sphere. They are conductor. Okay, and one is positively charged in the beginning, this is neutral. But if you join these two spheres using the nail, this is iron nail, okay, iron is a conductor. So what happened is certain amount of charge transfer there, like this. So this positive charge transferred there. So the charge transferred due to this nail here. So they are in contact actually by means of this nail. These two copper spheres, they are in contact. This is called as the conduction. Okay. So the conduction, you can observe conduction if two or more than two objects, they are in contact. But here I want to define new term, another term we call electrostatic induction. Electrostatic induction. What is this? So let us suppose this is a rod, like a copper rod. This is copper rod. Copper is a conductor, and this rod is positively charged. Let us suppose this rod is positively charged. You can make this positively charged using some source. Okay, and I would like to bring another rod, the second rod. This rod is again the copper rod, conductor. You can take copper or any other. So this is positively charged, and initially this is neutral. This is neutral rod. Now you bring the neutral rod close to the positively charged rod. Now what happened here is this end, which is close to the positively charged rod, this end becomes negatively charged, and this end, which is far from this positive charge, this end becomes positively charged. So what happened? You produce the charge here without touching. This phenomenon, this is called as the electrostatic induction. So the production of charge without touching, that is called as the electrostatic induction. So this is electrostatic induction, is production of charge without touching. Is called electrostatic induction. Again, look here. I said production of charge. In fact, I do not produce the charge here, but simply I separate the charge. In reality, the charge is not produced there, but still I use the word production. Actually, the charge only is separated here. What happens is, if you bring this positively charged rod close to the neutral rod, all electrons here, the electron is negatively charged, they are attracted by this positive charge. That's why the electron come to this side, and here on this side you have an excess of positively charged. So this end becomes positively charged, this end becomes negatively charged. You simply separate the charge, but still I use the word production. You can do that, okay? So you simply separate the charge. You do not produce, you separate the charge, and this is called as the induction, electrostatic induction. Production of charge, again don't confuse, production means here I separate the charge. The production of charge without touching, that is called as the electrostatic induction. For example, another one, let us suppose here you have a sphere, okay, this is a sphere, and let us suppose this is negatively charged, like this, and if you bring another sphere here, neutral sphere, okay, close, you have to bring very close to the, don't touch, but bring close to the negatively charged rod. Now what happens? This side becomes positively charged, and this side becomes negatively charged. This is also the electrostatic induction, same thing. So due to this charge, negatively charged, the positive charge developed on the side close to the negative charge. On this side, look, this side is close to the negative charge. That's why this side is positively charged and this side is negatively charged. Electrostatic induction. Okay, electrostatic induction. And here, this charge, due to this charge, positive charge developed, we call this is your inducing charge. This is inducing charge. Okay, and both these two, positive charge and negative charge, together you can call induced charge. Induced charge. Okay. So this is induced positive charge, this is induced negative charge, but here you have an inducing charge. Okay. So this is a, you can charge the object by bringing the neutral object close to the charged particle. Okay, charged object. Okay, so this is about the electrostatic induction, very brief discussion. Now let us talk about the force between the charged particles. I told you that a like charge they repel and unlike charge they attract. That means if you have a two object, let us suppose this is positively charged, simply you can write down Q. You can represent by Q, and this is my first charge, so you can write down Q1. And here is another charged object, this is, let's say, Q2, okay. And if this is positively charged and this is negatively charged, they attract because unlike charge they attract. So this is positive charge, this is negative charge, so they attract, okay. And if you bring this is positive and if this is also positive, both charge they are positive, they are like charge, then in this case the force between them is repulsive force, they repel to each other. That's why electrostatic force, you can have attractive as well as repulsive. So there is a force between two charged objects, two charged particles. So that is called as the electrostatic force, and that force is attractive as well as repulsive. If you have the similar charge, like charge, they repel, so that is a repulsive force. And if you have an unlike charge, dissimilar charge, they attract, we call that attractive force. It is, you can compare with the gravitational force. For example, let us suppose you have a mass m1 and you have a mass m2, and if they are at a distance d, there is an attractive force between two masses, and that attractive force we can call gravitational force, which is F of g. This is equal to uppercase G m1 m2 divided by d square. This is gravitational force, but please keep in mind the gravitational force is always attractive. The gravitational force is always attractive, and this is the formula to calculate the gravitational force. But here we are talking about the electrostatic force, or you can also call it Coulomb force. The Coulomb force is the force between two charged particles, okay, and the Coulomb force is attractive as well as repulsive. If you have the similar charge, like charge, you will have a repulsive force. If you have an unlike charge, two unlike charge, then in that case you will have attractive Coulomb force. Okay, so the Coulomb force or electrostatic force, that's the same thing. Now let us suppose I have two charges, I don't care plus or minus, I have two charges, because I said you have a attractive and repulsive, both are possible. It depends on the nature of the charge, okay. So I have two charges, Q1 and Q2, and there is a force between these two charged objects, okay. Let us consider the distance between them is d, same as this gravitational force, okay. Here I have two charges, Q1 and Q2, two charges, and they are at a distance d, and there is a force between these two charges. Depending on the nature of the force, you have attractive force or you can have repulsive force. If you have the unlike charge, you will have an attractive Coulomb force. If you have a like charge, you have a repulsive Coulomb force. Please don't confuse Coulomb force or electrostatic force. That's the same thing. Coulombs are force. So the electrostatic force between two charged particles is directly proportional to the product of the charges. Let me write down the electrostatic force between two charges is directly proportional to the product of charges and inversely proportional to square of the distance between them. This is called as the Coulomb's law. The force between the two charged particles, that is called as the Coulomb force, and this law is a Coulomb's law. So what is Coulomb's law? The Coulomb's law is electrostatic force between two charges is directly proportional to the product of charges and inversely proportional to the square of the distance between them. Same as this. This is a gravitational force. Look here. Gravitational force F of g, this is directly proportional to product of the charges, masses, m1 times m2. The gravitational force between two mass is directly proportional to the product of their masses, m1 times m2, and inversely proportional to the square of the distance between them. This is gravitational force. But here we are talking about the electrostatic force, or you can call Coulomb force. And the Coulomb force, let me write down F of c, this is Coulomb force, is directly proportional to the product of the charges Q1 times Q2. The electrostatic force or Coulomb force between two charged particles is directly proportional to the product of those two charges and inversely proportional to the square of the distance between them. Q1 times Q2 divided by d square. This is the distance between these two charged particles. So it is kind of similar to the gravitational force. Look, gravitational force is directly proportional to the product of their masses. The Coulomb force is directly proportional to the product of the charges, product of their charges, Q1 times Q2. And here gravitational force is inversely proportional to the square of the distance between two masses. Here the Coulomb force is inversely proportional to the square of the distance between two charges, kind of similar. So this is the Coulomb's law. F of c, or people they also write down like this, F of E, electrostatic force, Coulomb force. Okay, F of c is proportional to Q1 Q2 Q1 times Q2 divided by d square, or you can write down F of c. This is equal to, write down the K, this is electrostatic constant, K Q1 Q2 divided by d square. Here K, this is electrostatic constant, or you can call Coulomb constant, this K, electrostatic constant, or you can say Coulomb constant, and this is equal to K, this is equal to 9 times 10 to the power 9 Newton meter square per Coulomb square. This constant K is equal to 9 times 10 to the power 9 Newton meter square per Coulomb square. Look at this. In case of gravitational force, this universal gravitational constant, this number is G, this is equal to 6.67 times 10 to the power negative Newton meter square per kg square. This is gravitational constant, 6.67 times 10 to the power negative 11. But this is 9 times 10 to the power 9. This number is really big. This number is really small. That's why the electrostatic force, Coulomb force, is really bigger than the gravitational force. You can easily realize the Coulomb force, electric force, but it is really difficult to realize the gravitational force because this constant is 6.67 times 10 to the power negative 11 Newton meter square per kg square. But look here, in this case, the Coulomb constant is 9 times 10 to the power positive 9 Newton meter square per Coulomb square, and this is a big number. So this is the formula. Please note this. F of c, Coulomb force, is K times Q1 Q2 divided by d square. Q1 charge, Q2 charge, d is the distance between them. Look at d square. This is also called as the inverse square law, because if you take this d square up here, then it becomes d inverse of 2. So it is simply, we also call inverse square law, same as this. This is also inverse square law. Okay, so the Coulomb's law is K times Q1 Q2 divided by d square. The electrostatic force or Coulomb force between two charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Okay, so this gives you the magnitude of Coulomb force between two charged particles. Now, force, Coulomb force, gravitational force, whatever, the force is a vector quantity. So how do you give the direction. For example, this is one charge and this is another charge, and the direction is, you can get the direction just simply by drawing the line like this. Draw the straight line like this, like this. The line joining them, the line joining the two charged particles, that gives you the direction. But how? It depends. Let us suppose this is positive charge, this is also positive charge. So what is the direction of the Coulomb force then? So the direction of Coulomb force is away from each other like this. This is the direction of Coulomb force, this is the direction of Coulomb force. Because if you have the similar charge, then in that case, if you have the similar charge, then in that case, they repel to each other. That's why you have to draw like this. If you have here, let us suppose this is negative charge and this is positive charge, what happened? Then the direction is like this. They attract to each other. So again, you draw the line like this, and this, because they attract to each other. So this is the direction of the force on this object, and this is the direction of this of the Coulomb force on this object, these particles. Okay, so the line joining the two charged particles, that gives you the direction of the Coulomb force, electrostatic force. But keep in mind, if you have the similar charge, they repel, and in that case you have to draw the line like this. You have to draw the vector like this. If you have a dissimilar charge, unlike that, draw the direction like this. They attract to each other. Okay, so this is about the Coulomb force, electrostatic force. And we have another term we call the electric field. Electric field, this is simply denoted by uppercase E, and this is a vector quantity. So what is electric field? For example, let us suppose this is one plate, and this plate is, let us consider, positively charged. This is positively charged. And here you have another plate, second plate, and this plate is negatively charged. Negatively charged. Okay. Then if you take one tiny particle, like let's say electron, if you bring the electron like this is an electron. And okay, consider, take one electron, this is electron, and you keep here, you hold the electron there. Now if you release the electron, what happens? Look, this is negative charge, this is positive charge. So simply this electron goes down then. This negative charge repel this negative charge, but this positive charge attract this negative charge. That's why it goes down. But what happened in this case then? If you take the positive charge here, what happened in this case then? This is positive charge, this is also positive charge, but here you have a negative charge. So this negative charge attracts this positive charge. Is that right? So if you keep the bring the charged particle inside the electric field, for example, let us suppose here you have one charged particle, charged object Q, we call the source charge. Then you can observe, you can measure its effect around here, like somewhere there. You can feel the effect of the charge here. And if you take another tiny charge here, it is tiny, small, we call the test charge. We call test charge. And this test charge, it experiences the force due to this source charge. This is test charge, this is your source charge. Source charge, okay? So the force experienced by this test charge, that is called as the force per unit test charge. That is called as the electric field. So you can write down electric field E, this is equal to force per unit test charge. So this is how you define the electric field. Force per unit test charge. So that is the electric field. And electric field is a vector quantity. So you have to give the direction, and the direction of electric field is always from positive charge to negative charge, like this. This is the direction of electric field. Electric field is always from positive charge to negative charge, from positive terminal to negative terminal, like the positive plate to negative plate. Okay, so electric field E, it is a vector quantity, force per unit, test charge Q 0. This is how we define. But simply you can also write down like this: electric field E, you can simply write down force divided by charge. This is also one. Okay, you can use this formula also. Here just to define, I use the little charge, tiny charge. This is a test charge, we call this. This is how we define. Or you can write down this way also. And again, the electric field vector quantity, it is the vector quantity, and the direction is always from positive plate to negative plate, or from positive charge to negative charge. Okay. Now look at this. Let us suppose you have this is your source charge. Let me call this is a Q. And you take another very small charge, that is how we define the test charge. Here you have a Q0. This is test charge. And the distance between them is, let's say, D. You can use a Coulomb's formula. F of, this is your Coulomb force, F of C, okay. You know the F of C is K, Q1 is Q, Q2 is Q0. You can do this. And the distance between them is D square. So if you want to figure out the force between these two charge particles, this is a source charge, this is a test charge. But we have a formula, the Coulomb force is K, Coulomb constant, times Q1, here Q1 is Q, Q2 is Q0, and the distance between them is D, so you have to write down K, Q0 divided by D square. Now plug here, E equal, look at this, F of C is K, Q0, divide this by D square. This is your force, divide by test charge is Q0, right? Now you can cancel this Q0 and Q0. So what is this then? What is your electric field? Then E, this is, you can also write down K, Q divided by D square. This is another formula. Okay, this is also, you can use this formula or you can also use this formula. KQ, this gives you just the magnitude only. E equal to KQ divide this by this. So what is Q? Q is the source charge, magnitude of the source charge. This is the distance between this test charge and the source charge. So KQ divided by D square. This is a formula to calculate the electric field, and this source charge, this is a point charge. So this formula is good to calculate the electric field due to the point charge. And you know that the electric field is always defined at a point. So right here at this point, if you want to define the electric field, so this point is at a distance D from the source charge. Okay, so electric field at this point is E, this is equal to K times Q divided by D square. This is the distance from here to this point. Q is this charge. This is a point charge. Point charge, not like the extended object. It is a point charge, and Q is the magnitude of the charge. D is the distance, and K is a constant. So this is the electric field due to the point charge. This electric field at a point due to point charge, at a point due to point charge. We can say the object, this charge particle, it is really small. That is what we call the point charge. So electric field force per unit test charge, that is the electric field. This formula, this is the electric field due to the point charge. And electric field, it is a vector quantity, you know that, and the direction of electric field is always from positive to negative charge. Coulomb force, it is not always from positive to negative. It depends, like if you have a similar charge or if you have the dissimilar charge, accordingly you have to figure out the direction of the Coulomb force. But the electric field is always from positive to negative charge. Keep in mind, the direction of electric field is always from positive to negative charge. Okay, and look at this. The definition is Coulomb force divided by test charge. That is your electric field. And if you want to write down the unit, the force is Newton, charge is Coulomb. So Newton per Coulomb. That is the unit of electric field. Okay, the unit of electric field is Newton per Coulomb, or there is another one, another formula is volt per meter also, but by definition you can use this, or you can also use this volt per meter. Okay, so for example, let us suppose this is the positive charge here, and this is a negative charge. So what is the direction of electric field? This is the direction of electric field. So this way. So what is the direction of force then? Force is this way also. Force on this charge is this way, because this charge is attracted by this charge. Okay. So sometimes the direction of electric field and direction of electrostatic force, they are similar, but sometimes they are different. Okay, so they are different. For example, like if you have a plus charge here, if you have a plus charge there, in this case the electric field is in this direction, and the force is also in the same direction, because this this charge and this charge, they repel. So in this case the direction of electric field is also away from the positive charge, and the force is also away from the charge. So it's same direction, but in this case it is different. Okay, now if you have, let's say, positive charge here, and let us suppose you have negative charge there, and if you release, let's say, positive charge from here, we call unit positive charge. What happens if you release the charge from here? Simply charge goes follow this path, this line, follow this path followed by the unit positive test charge, path followed by the test charge in the electric field is called electric lines of force. Path followed by the test charge. We simply test charge, we take the positive charge. Okay, unit positive test charge. So if you release this charge particle here, this is positive, this is negative, and so what happens? This charge repels this positive charge, so it follows this path. Okay, if you release somewhere from here, like somewhere from there, it goes something like this. This is also the electric lines of force. You can draw another one. This is also electric lines of force, like this, starting from positive charge and terminating here at the negative charge. So this is electric lines of force, this is electric lines of force. Or you can draw electric lines of force like this. You can draw as many as you want, like this. So all they are electric lines of force. So what are the property of electric lines of force? You can say that electric lines of force, start from positive charge and terminate at the negative charge. So you start from positive charge and terminate at the negative charge. That's the first property. And the second property is the electric lines of force, they never intersect to each other. The electric lines of force never intersect to each other. Another property, let me write down, like right here. This is the, what is this? This is the electric lines of force. This is the electric lines of force from positive to negative. That's why you have a pointer there. So if you choose this point, and if you draw the tangent here like this is a tangent. So this tangent line gives you the electric field at this point. If you draw the tangent at any point on the electric lines of force, the tangent line that gives you the electric field at that point. If you choose the point here, for example, here, okay, and if you draw the tangent like this, so this gives you the electric field at this point. So that is the second point. So second point you can write down the tangent drawn at any point on the electric lines of force gives electric field at that point. So this is another property, you can say second property. And third property is, like, let us suppose this is one electric lines of force. You cannot draw the second one like this. Second electric lines of force, look, they intersect here, this, like this. Two electric lines of force, they intersect. But this is not possible. This is not possible. So you cannot do this. Two electric lines of force, they never intersect with each other. Two electric lines of force, they never intersect. That is not possible. So your another property is two or more than two electric lines of force never intersect to each other. Your third property is two or more than two electric lines of force never intersect to each other. Why? What happened? For example, let us suppose this is one electric line of force. Another electric line of force is, if it is possible, like this. Suppose they intersect. Suppose, okay. And at the point of intersection, look at this. The first line of force, this. If you draw the tangent, this is E1, electric field right here. And for the second line of force, this one, okay. Then if you draw the tangent here, then you have E2 then. At the point of intersection, you will get two electric field, which is not possible. That's why two electric lines of force, they never intersect to each other, because at the point of intersection, you will get two electric field, which is impossible, which is not possible. So two or more than two electric lines of force, they never intersect to each other, never intersect to each other. Okay. There are many, I don't write down all of them, I wrote a few important only. So this is positively charged, this is negatively charged, and if you want to draw the electric lines of force, you can draw like this. If you have many, you can do this way, starting from positively charged and terminating here at the negative charge. Okay, so this is the electric lines of force. Then you can see that the electric lines of force, they are crowded near the charge. The electric lines of force, they are concentrated here, they are concentrated there. So electric lines of force, they are crowded near the charge. The concentration is higher there, big there. So here, if you have more electric lines of force here, that means your electric field is big here. Electric field is big, like there, that where the electric lines of force concentrated, there at that area, that point, you have a bigger electric lines of force. But if they are diverged, like somewhere here, the electric field is smaller. Or in another word, you can say that if you are close to the charged particle, electric field is big. If you are very far from the charged particle, the electric field is very small. Okay, so electric lines of force, they are crowded near the charged particle. And another one is like, if you have only one charge, like let us suppose, if you have just the one charge, we call monopole. This is, let us suppose, positive charge. We call monopole, just one charge. I don't have a negative charge there. How do you draw the electric lines of force? If I give you this charge, positively charge, how do you draw the electric lines of force? Just you have only one charge. We call monopole. We call monopole. Only one charge, that is called monopole. If you have two equal and opposite charge like this, positive charge, and you have negative, two equal and opposite charge. If you separate at a certain distance t, this is simply called as the dipole. Okay, I'm talking about the monopole here. So how do you draw the electric lines of force? I told you that the electric lines of force originating from positive charge. So in this case, simply draw like this. Your pointer, it goes like this, away from the charge, because the electric lines of force, they start from the positive charge. If you have a monopole, positively charged, you have to draw like this. And if you have negative charge, just the negative charge only, like this is negative charge. In this case, you have to draw the same way, okay, but in case of positive charge, the electric lines of force start from the positive charge, that's why your pointer is away from the charge. But in case of negative charge, the electric lines of force, they are terminating here, so you have to draw the arrow pointer like this. Like this. So this is the electric lines of force. Look here, the electric lines of force is coming toward the negative charge. In this case, the electric lines of force are moving away from the positive charge. And these electric lines of force, this line, they terminate somewhere where you have a negative charge. If I look at this, if this is a proton, for example, if I release here, this proton will go somewhere where this proton can meet the negative charge. Okay, so here also I have only positive charge, so the electric line supports one charge. Look, this line, it goes somewhere where you can meet the negative charge. Okay, so this is how you draw the electric lines of force. Okay, electric lines of force. Okay, so this is about the charge, Coulomb's law or electrostatic force, electric field. Okay, next we have to talk about the electric potential. Okay, electric potential. Simply it is denoted by V, and electric potential, it is the scalar quantity. It measures in volt. But you know what happened, my video is kind of long, so I'll bring another video. Please watch my next video to understand the electric potential. Okay, so I want to stop this video right here. Thank you.